Okay, so on this, what is it called? A 5 for a 5, AP Calculus Day 2. So here what we're doing is we're looking at a graph of F prime, and then a table, and it says that F is twice differentiable, and it's also got F of 1 is equal to negative 2. It tells me something about being able to use the fundamental theorem with F prime. And then I've got a table of values with G of X and G prime of X. So the function G is twice differentiable, and selected values are shown in the table. So first thing I do with the AB1 is I look at the fact that we are looking at the open interval from -3 to 8, for which the graph has horizontal tangent lines. So which the graph of F has horizontal tangent line, has a horizontal tangent line or more. For each value X, determine whether F has a relative minimum, relative maximum, or neither a minimum or no maximum. Now, I wrote some things out here, and I'm just going to kind of stick with it because in the interest of time and a recording. So first thing I'm going to do is I'm going to look at the critical numbers are X is equal to 1 and 6. So if you look at it, it's where F prime is equal to 0, and that occurs right here and here at X is equal to 1 and X is equal to 6. Now, if you notice, there's some pluses or minuses on your graph, and I'm thinking you put them there. So let's try to walk through this. I want to know next if, well, I've got horizontal tangent lines, all right? So for each value of X, determine whether F has a relative min or max at that point, or neither. So I set those critical numbers out on the number line, and all I'm going to do is evaluate the graph. So if you look at this, I've got the pluses. I've transferred the pluses that you have here to here. And the minus goes here from 1 to 6. So I'm looking at from 1 to 6, F prime is negative. And then from 6 to 8, F prime is then positive. So if I'm looking at these, I've got signs of F prime that I'm working with. And then I can extrapolate about the F values or the function values. So I know that if the derivative is positive, I know that F is increasing. And I know that if the derivative is negative, I know that F is decreasing. And if it's positive again, we know that F is increasing. Okay, so we have that much information. So we just have to say where there is a local min or max. And so all I did very simply here is I said a local max exists. A local max exists at X is equal to 1 as F goes from positive to negative at X is equal to 1. So it makes that kind of hill kind of thing where there's a maximum point at the top. Then a local minimum exists at X is equal to 6 as F prime goes from negative to positive at X is equal to 6. Okay, so that's where our local min exists. We have a local max at 1. We have a local min at X is equal to 6. Okay, the next problem asks for minimums, the minimum of a graph. And with the minimum of a graph, when they speak like that, it's really that what you want the lowest point on the entire graph. So that point has to do with the extreme value theorem. That point that we're talking about for the minimum value is the lowest value on all the graph. And remember that if you drew a graph like this, that we would have a minimum that exists at the end point. And then here's a local, and there's no max. Here's a local max, and here's a local min. So there's no max, but there is an absolute minimum value on there. So you have to be careful when you just dismiss the endpoints and just start talking about the derivative right away. Okay, let me take this off. So then to conclude this problem, then all we're going to do is we're going to say, all right, find the minimum value. We are going to compare the following. Now, rather than go in and draw the picture, I'm going to say this and then we'll review it quickly. So what you want to do is compare F, is it F? Yep. F of the critical numbers with F of the end points. So I've got F of the critical numbers, F of 1. I got to compare F of 1, F of 6, because those are people that are people in the open interval that we know that they're locals, but are they absolutes? So then F of 6, and then you have F of -3, then also jumping in there with F of 8. So what these we hope to do with these is to find out the value. We already know f of 1 because it's given in the problem. And with f of 1, we have that's negative 2. So we have negative 2 for f of 1. I think my pen might be. So negative 2 for that. Now, f of 6. Let's do a little shorthand work here. We know that f of 1 is negative 2. So f of 6 minus f of 1 is equal to the integral from 1 to 6 of f prime of x dx. So if I want to find out what f of 6 is, because I've got to compare these and say whichever one is the biggest is the biggest, whichever one is the lowest, the smallest is the minimum value, and that's it. I'm just dealing with minimum value of f on the closed interval. So if I look at these and I find value of f of 6, here, let's go up here. I've got this equation to give me a start. So now f of 6 is what we're looking for, right? And then minus, and if we're talking about it, what are the units on the x value here? Is that important? I don't really see it there. Not really. For each value of x, there, I think they're just working with a function for this. So getting back to the values that I have here, we have this relationship that exists, and we could say, all right, well, we can sell this, we can bottle it, we can put this as f of 6, we want to find the value of, is equal to negative 2, because f of 1 is negative 2. And then we have plus the integral from 1 to 6 of f prime of x dx. So if I look at the area from 1 to 2, one to six, it looks like this. So since you're going in an ordering property, you're moving forward, then all we have to do is say, okay, well, then that's just equal to negative 2 plus the actual area for 1 to 6, which is, the area is 14, but it's negative 14 because it lies underneath the x-axis. So negative 14, and we have an answer then of negative 16. Okay. All right, I'm going to take a break in here and come back with number 5 and last comments. Okay.